I hope everybody can see the screen again with a different paper title. So this is detection of ICMPv6 DDoS attacks using hybrid integration model, that is with RNN and GRU. Sorry, you can't see.
It's not moving.
Yeah. Yeah, you can see that.
Yeah, that's good.
Slide.
You can use that one. Yeah.
Can you see?
Yes, we can see. Go ahead.
So the aim is that this research aims to propose a new DDoS detection by combination of using deep neural network RNN and GRU. And then hypothesis: can these two combinations of RNN with GRU be successful fused to prove a robust model and fit for the detection of ICMPv6 DDoS attacks? The literature review identified a specific research paper detailed below that similarly supports the proposed model. So as I had given you, this paper has given promising results where the author has used NSL-KDD datasets and he achieved 99.20% of detection of DDoS attacks. But I should remind that this combination is with CNN and LSTM. So now object is designing the solution model using data sets specifically based on ICMPv6, generating ICMPv6 DDoS attacks, datasets using VMware in laptop, validating the proposed technique by comparing with the Issa model on 3 datasets using performance metrics like accuracy. So in this paper, I had just used only one performance metric, that is accuracy. Evaluate experiments against the state-of-the-art DDoS detections. So a novel approach that detects DDoS attacks based on deep neural network combination of RNN with GRU that determines the attack, generating ICMPv6 DDoS attacks datasets, evaluation of proposed solution model by comparing the obtained metrics of the combination with state of the art to determine whether the proposed model is robust and best fit for the learning and detection of DDoS attacks. So problem statement, the threat actors utilize covert intrusion techniques to operate discreetly. In the early phase, they are driven to develop unique attack patterns without identifying signatures or exploit vulnerabilities in network protocols, and the enterprise network ultimately comprising the data compromise the target server. By misusing of fragmentation technique, an attacker can bypass detection and perform attacks. In a fragmentation attack, the attacker designs the attack where an IDS handles fragments that cannot be detected. So, for example, like the first fragment packet with synchronization equal to 0, acknowledgement equal to 1, and offset equal to 0 arrives at the firewall or intrusion detection system. It passes, however, the second fragment is different from the first fragment, which could not be the same sequence or the same values. So to avoid these ICMP attacks, then one can say that why can't we disable ICMP in the network? So that would be the best security where each and every enterprise or each and every network can have, but it has its own consequences. So because of that, if you disable, then troubleshooting cannot be done properly, and then ping and trace routes cannot be used because there are very much key commands which can provide you the information about the establishment of the network and the alive of other systems that are working in your network. And then If you use like MTU paths function correct, it won't work or function properly. So it may lead to fragmentation issues and degrade the performance. So reachability, destination unreachable messages won't be sent to find out whether communication between nodes or systems can communicate, and also to test any issues in establishing the connections. So now this is a basic OSI model. I'm not going through each and everything. I'll just give you a one-line gist so that you can understand from the on the block diagram. So from the bottom of the layer we start, that is from the physical layer, and then we'll go up to the application layer. So we totally have 7 layers. The first one is the transmit information in the raw bit stream format over a physical medium. So it could be all your cables through which the electrical pulses are being transferred. And when you get into the system, it is translated, or you can say converted into zeros and ones. So data link layer, it specifies the format related to the frames in the network. It is divided into 2 layers, the media access control, which controls device interaction, and the logical link control, which focus on the addressing and multiplexing. So people who sit at the system would not be able to understand what exactly is this, but people who are in the networking domains, they can understand very easily, especially in the core domain that is related to Cisco networks or firewall devices like switches, routers, and then firewalls. Then they will be able to understand what exactly this terminology is. And then network layer determines the shortest path for the packets to be routed in the network and concentrates on the IP protocol. Transmission layer, this layer manages to ensure that the segments are in sequence with error-free. This includes port numbering and the use of TCP and UDP protocols. Session layer manages session related to setup, authentication, connection, reconnection, and termination. And presentation layer, it is responsible for managing, translating, encoding, decoding, encryption, and decryption information as required by an application. Application layer, this layer is to manage the information in your readable format by accessing the service of the previous layers. Okay, and we have types of fragment attacks, that is fragmentation attacks levels. So I had listed over here 3 most of the time. So DOS and DDoS attacks, IDS flooding, tiny fragment attack, teardrop attacks. So what happens in IDS flooding? IDS flooding is a technique used by attackers to overwhelm or saturate an IDS, making it ineffective at identifying and responding to legitimate threat. And IDS is a security tool designed to monitor network traffic and identify suspicious or malicious activities. It does so by analyzing patterns and signature of known attacks, DDoS and DDoS attacks. And then second is, I think I have gone. Okay. Tiny fragment attack. A tiny fragment DDoS attack likely refers to a type of distributed denial of service attack that involves sending extremely small or fragmented packets to a target server or a network with the intention of overwhelming its resources. This type of attack can be challenging to detect and mitigate because it relies on fragmenting network packets into very small pieces, making it more difficult to traditional network defense to identify and filter out malicious traffic. And moreover, it is kind of attack that is what you call done from various systems. And the first thing is to know what are the malicious systems that are being corrupted or compromised. So it is a bit time-taking process to identify these. So we should be very careful. And teardrop attack. Teardrop attacks is a type of denial of service attacks that exploits a vulnerability in a target system, operating system, or a network attack. Network stack. Sorry, it gets its name from the way it fragments the packets of data it sends to the target, making them appear as if they reassemble a teardrop. This type of attack was more prevalent in 1990s and early 2000, but is now mostly a historical difference because modern operating systems and network equipments have largely mitigated this vulnerability. And if you can see the other diagram where an threat attacker is trying to compromise the system in the enterprise network, and from there he is trying to access the server and trying to flood all the packets with malicious software or command and control through which what you call so much of traffic is being diverted onto the server. It could be a simple packets or it could be a large packets, and the sources of the server is being exhausted, and most probably the DNS service is being crashed, and then the other legitimate users on the right side will not be able to access the server. So what is the statistics of the attacks? From CrowdStrike second quarter of 2024 statistics, it is clear that despite a 49% decrease quarter over quarter, DNS-based DDoS attacks remain the most common attack vector, with a combined share of 33.9% for DNS floods and DNS amplification attacks. Chin flood came in second place with a share of 22.9%, followed by RST floods accounting for a little over 10.4%. Chin floods and RST floods are both types of TCP-based DDoS attacks. DDoS attacks are related to layer 3 attacks, still account for 38% of the total, whereas ICMP-related DDoS attacks occupy 2.3% alongside other types of attacks such as TCP, UDP, and RST floods. On the face of it, understand that DDoS attacks exist and are one of the deadliest attacks where the IT cyber security industry is still suffering. And this is the model that has been introduced by Ahmed Issa. He has proposed this model, which is CNN and an LSTM. So it's like the model was designed with 7 layers of deep neural network consisting of CNN 1D with the kernel stripes in CNN layer, max pooling 1D with activation function, ReLU, and softmax for the output connected layers. His model was evaluated using the NSL-KDD datasets that consist of 40 features with multiple attacks, achieving an impressive accuracy rate of 99.20. Figure illustrates the Issa model architecture. And then this is the proposed model where it consists of 9 layers of network, starting with the RNN layer. That is you can consider the second layer. Input layer is the layer where data sets are being provided. And then GRU, it is followed by a GRU and max pooling layers, and a flatten, dropout, and then a dense layer are used in this architecture. And then the proposed model presents a hybrid approach, merging RNN and GRU components into a unified architecture comprising 9 layers, which is illustrated in figure. This integrates aims to enhance the efficacy of DDoS attack detection. Normally, in each model, input layer and an output layer are present. In between, there exists a hidden layer of the model design by arranging them depending upon the chosen algorithm and respective activation function ReLU. At the required layer, the 14 parameters are the network attributes used to improve the output of the model. At any given time t, the current input is a combination of input at t, that is time, and input layer t minus 1. The output at any given time is fetched back to the network to improve on the output. The model architecture starts with an initial input layer consisting of an RNN with a kernel filters of 128, utilizing the rectified linear unit, that is activation function. Following this, a GRU layer is employed with 64 filters, maintaining sequential order. The third layer comprises a max pooling layer and a one-dimensional convolution layer with a pooling size of 1. Subsequently, a flattened layer reshapes the tensor into a vector, facilitating a seamless transition between connected layers, particularly interfacing with the dense layer. Proper regulation is then applied, randomly deactivating 10% of the neurons in a layer during training to mitigate overfitting. The final layer is a dense layer designed for classification tasks. The output of this dense layer typically undergoes a leaky ReLU activation function, generating probabilities for each class, such as normal and an attack. So now so what is an RNN? The basic operation of an RNN involves iterating over a sequence of inputs while updating the hidden state at each step. This hidden state is passed along from one step to the next, allowing the network to maintain information about previous inputs. Mathematically, the hidden state at the time step t is a function of the input time step t and the previous hidden state. So ht equals to f of ht minus 1 xt, where ht is a hidden state at time step t and ht minus 1 is a hidden state at time step t minus 1. That is the previous hidden state. xt is the input at the time step t. So a simple example over here is quoted over here. So C0 equals to John or June. C1 equals to finance or French. So France or French. So if you make a sentence out of it, John lived in France for a long time and speaks French fluently. Who lived in France? That is the context when it come across the computation. So depending upon the context, it has to remember whether it is John or it is June, depending upon the value that is been assigned at that point of time. So June can speak French fluently as it is her mother tongue. So now in this context, what would be the value of the C0? So in the similar way, what would be the value of C1? So that is how the RNN has to remember. But because of the gradient descent problem, it may diminish these values as it goes forward. So in order to do that, in order to retain those values, we are going for GRU. So what does the GRU do? Let us see. So GRU is a faster and more efficient. It is explicitly resolves the vanishing and exploding gradient problems. It reduces the usage of gates to using less memory. So first thing is it reduces the consumption of the memory, and at the same time it also provides the contextual retaining of the information that needs at that point of time to take exact decision and provide the output. So for the hidden state update, the core function of the GRU is to maintain a hidden state vector which stores information about the sequence it has seen so far. The hidden state is updated at each time step based on the current input and the previous hidden state. Gating mechanism, GRU incorporates a gating mechanism that helps control the flow of information through the network. This gating mechanism consists of two gates, that is reset gate and an update gate. So it has to maintain when to use the reset gate and when to use the update gate. So when is reset gate used determines which information from the previous state should be forgotten or reset. Similarly, the update gate controls how much of the information that is new state is a blend of the old state, and then that is the output to the new state. Okay. So further, if you see, the update gate helps the model decide how much of the new candidate state to retain. That means a value close to 1 implies keeping a lot of new information, while a value close to 0 means relying more on the old state. So candidate, that means based on that, the reset gate and the new update gate both will be acting depending upon the context. So this way, it's like the GRU will be supporting for the long dependencies information that need to be retained. Okay. And then you can see from the this picture, you can understand clearly. So normal neural network, what happens as it moves forward, the information that is from the middle node, that is the node that indicates whether this network can be retaining or not. And if you see the GRU and LSTM network, it is in the dark. That means it based on these two combinations of the gates, it tries to accommodate that information to be retained for a long time, so that the appropriate decisions can be taken, and at the same time the related output can be provided, which needs to be either it could be a classification or it could be a clustering based on it's a normal attack or a normal or an attack. So what are the advantages? So RNN and GRU could be used together in a DDoS attack detection, with RNN focusing on flow patterns and time to determine an attack, whereas GRU can keep track of required information that needs to be detained based on the context, that is for long dependencies. And similarly, in the DDoS attack prediction, and RNN could identify malicious packets of traffic based on the features, where RNN is used in conjunction with the time series of traffic flow to make DDoS attacks prediction, where GRU supports in updating the necessary information based on the two gates, reset gate and the update gate, avoiding the vanishing gradient problem. So now coming to the data sets, so we have two, before jumping into the data sets, let us see what is IPv4 and IPv6 differences, because there is a lot of differences between these two, and there are so many vulnerabilities. I'm not sure whether I had provided the vulnerabilities over here, but differences wise, if you see, it makes a lot of difference, because when the data has been fed or loaded into the model, it also depends upon the size. It also depends upon the what type of features and number of features, and at the same time, each feature how much what to call memory of bits it is going to occupy. So let us see a couple of them, because I have to rush to complete this. So version IPv4 and IPv6 address size 32 bits, and this occupies 128 bits. Notation integer IP address for format 4 lot. It's an integer kind of thing. So if you see the what you call IP address itself, you can see it is being represented with a dot notation, and whereas in the IPv6 it is denoted with a colon notation. And loopback addresses, it's 127.0.0.1, and it's a double colon 1. And the notation of colons and the dots also it's like plays a significant over here. So when you have zeros in the whole octet, you can just represent it with the 1 0, or you can present with only just a column. So that means the previous octets, it all are 0. So it's only one it is consisting of. So it has been represented in that format. So requires address translation for IPv4, but it is not required for IPv6. And then packet addressing, unicast, broadcast, and multicast. But whereas in IPv6, you got unicast, multicast, and anycast. So address configuration, manual DHCP is done in IPv4, but whereas in internet, that is IPv6, you got auto configuration on devices using stateless address auto configurations. DHCPv6 is also supported for stateful connections. I think the table is self-explanatory. Please go through it if you don't mind. I'm just moving to the next slide. So data sets. So these are the fields of the echo request and echo reply messages. So as I discussed in my beginning of my presentations, which is in the previous one and in this. So I am just concentrating more on the ICMPv6 messages when an attack can be occurred at the time of finding the system is present or not, where connection is present or not, whether it can be established connection or not. For that we use ping. So with the same ping command, we can use ICMPv6 echo request and echo reply. Based on that, we can bombard so much of traffic using either a command and control or a specific DDoS attack tool. In the previous slides, we had seen hping is one tool that you can use, and then command and SCAPI scripting is also used for this kind of attacks. And what is the format of the packet is that you got type, code, checksum, identifier, sequence number, and data. And coming to the type, it is being clearly given that type 1, 2, 3, 4, 128, 129 is the main type code used for echo reply and echo request. And then, sorry, echo request and echo reply. And the others are also used for a similar kind of ping packet purposes. And then if you're coming to the various attacks that can be performed based on these type codes, it is being given by Ali, the other author. So source addressing, spoofing, and pure flooding. So in this, he has given the clear type codes and messages names also. So it's represents the message name, and at the same time, what kind of attack can be performed on this. So most of them from this, we can see reflection application, protocol exploit, and flooding. These are the three main attacks that can be viewed from this author who have provided. And then moving to next slide. So data sets. So as you can see, the table provides all different kind of data sets, right from Qaeda 2007, Qaeda DDoS attacks 2007, ISCX 2012, CIC DOS 20, NSL-KDD, and then you got Mavi, and then you got DARPA. So these are the categories of data sets that are available openly. However, to be noted, these are all IPv4 version. Most of them doesn't have any IPv6 variants. So for that purpose, we try to generate an ICMPv6 datasets in the laptop itself using a VMware, launching 4 systems, out of which one system is Windows Server 2016, targeting that from another 2 systems where Windows Server 2016 has a Wireshark to capture the traffic, and from Windows VPC1, and that is Virtual PC1, Virtual PC2, and Virtual PC3. So Virtual PC2 and Virtual PC3, we had launched a Scapy script and launched the attack. And from these two, we had generated very high amount of traffic, which could be treated equivalent to a volumetric data attack. And then from Virtual PC1, we are trying to figure out whether that DNS is able to provide the services or not. When we cannot get the connection response, that implies that the server is down and the attack has been successfully launched and met the objective. So this is what we had configured, and this all has done using VMware under one single NIC on the single laptop. And then you got once we got the captured data sets that is being in the Wireshark, that has transferred into a CSV file with these labels: time, source address, destination address, target address, protocol length, type, port, type 1, hop limit, payload length, next header, frame number, information. These are the 14 features which we had taken into consideration. And to be noted, I have not used any computing to extract the features. I have selected all the manual, mostly focusing on the header fields that are shown in the earlier slides. So this is the process, data processing that we have done. So cleaning, it has undergone cleaning, data transformation, feature selection, data normalization, data splitting, and imbalanced data. So these are the results. So what we have done is, first, these are the 3 data sets that we have selected. One is from NSL-KDD, where the author Issa Ahmed has used the same data set. And from there, and Mendeley dataset, that is both are IPv4 version. And because we are not able to find an openly available ICMPv6, it's like a Sain Malaysian, Omar Ilheja, he was using it's like ICMPv6 dataset for his own research. So we requested his dataset and try to use them in the same model that Issa Ahmed has come up with. So the same architecture, same model that we had implemented in using RNN and GRU. Whereas he has used that in the CNN and LSTM, but we need to, actually we had done both also. And these are the results. For CNN LSTM, as per the Issa Ahmed, we got 80%. And from Mendeley, we got 97.01%, and Sain Malaysian, we got 72.89%. And using the same similar kind of model architecture where Issa Ahmed has used, the same thing we had used over here, and used the same data sets. And the results were, for NSL-KDD, it's the same percentage of accuracy we are able to achieve. And for the Mendeley, we achieved 95.06, and for Sain Malaysian, we got 64.94%. So there is a vast variation in the results. So after generating the data sets, we had used our own proposed model, and at the same time compared with the Issa model. So our own proposed model, in a sense, the architecture that I had shown you over here. This is the architecture which I had used. So this architecture I had deployed, used it on the generated lab data sets, laptop data sets. So this is how the results were. So for if you compare Issa model with proposed model, for the CNN LSTM, we got 94.47%, and with respect to the comparing with the proposed model, we got 99.36%. Whereas for RNN and GRU, we got 94.5%, and for our proposed one, 94.48, where we are falling short of 0.2, I mean to say. Okay. And then this is the graph based on the epochs and accuracy I have taken, and area under curve also I have taken. So these are the graphs, but for the last graph, it seems to be a little bit distorted, which needs a room to improvise that. And then statistic based on all 4 data sets and comprising Issa model and the proposed model. So this statistics is based on all the 4 data sets. So if you compare again, 94.47 Issa model and 94.50 for RNN and GRU, and in proposed model we got 99.36%, and in for RNN and GRU we got 94.48%. And whereas in the NSL-KDD and Mendeley datasets and Sain Malaysian already provided the results and repeated. So this is the differences. But whereas in the state of the art, if you see, my proposed model results are very less. But however, I can assure you that the model is robust enough to detect the DDoS attacks, because any model that gives more than 50% is very robust and it is successful. So, but when compared to the state of the art, my model is very less, where I had also provided some more techniques where I had extended the score to a very high score, which I got 99.97 and 99.89%. Along with LTM data sets, I also generated another set of data sets in the lab itself from our university. So those 2 data sets are used and deployed the model, and this percentage of that is 94.58% is being extended, and which is far better than all the other authors. So that I'm putting it in another paper. So as of now, the conclusion part, the following are some areas where RNN and GRU combination can be applied for gaps or issues that can be treated as future research. Identification of objects, sequence related to traffic data, handling historical patterns, phishing detection, network traffic prediction and capacity planning, traffic analysis and anomaly detection, distinguishing between normal traffic and the potential threat, bandwidth allocation, optimization, routing protocols, avoid congestion in the network and also predict abnormality. This combination can also deploy in other domains like health monitoring, video analysis, speech recognition, natural language processing, real-time driving, decision making, forecasting, stock market prediction, etc. So that is all from my side. If you have any questions, please. You are very good.
Yeah, I do have a quick question.
Yeah.
I'll ask this question now. Then but so back to the NNs. So for semi-supervised machine ML, does the raw data and hierarchical clustering need to be structured or unstructured?
The hierarchical.
So yeah, does the raw data and hierarchical clustering, does that need to be structured or unstructured?
The raw data itself is unstructured raw data.
Oh, really?
Yeah. So the raw data itself is unstructured. You can't see any structure over there.
Yeah.
So you can't find out what structure it has. So possibly if you can mix it with the labeled data. As I said, semi-DNN supervised, so that we can make it as a structured and unstructured both. So from the unstructured, we can make it a structured. You know what I mean? Based on the known label. If you don't know what exactly it is consisting of, how do you do the structure? Am I right?
But you would, because I know that you can use, algorithms, to rule it.
No, I got your point, what you're saying. So what I mean to
So
say
you
is
can
that,
use pattern matching and all this stuff.
Yeah.
To find and structure it, and
Yeah.
then operating on that, can still be raw data, even though structured.
Yes, that's.
No, actually, I'm trying to say that, the structured one. So when you know the pattern, that means you already know the label. Am I right? So you know the parameter, one parameter. So that is what I'm saying. Once you know some parameters, based on that, you can structure the raw data or whatever data you want. So that is what I'm trying to explain.
And also, a quick question, just to surface the question, with these applicants and SIM, with the applicants in, with the DDoS, right? There's SIM DDoS
Yeah.
and anti-DDoS. Is that a subset of? Because you also mentioned TCP DDoS. Is that a subset of that, or
Which
is it
one?
separate?
Which one?
With this, you know how you said there's a SIM DDoS.
Yeah,
In slide.
yeah,
There was a SIM DDoS and there was a ACK DDoS. So that
Acknowledgement, yeah.
Yeah, is that just a subset of TCP? Because you also mentioned TCP afterwards, or is it a separate?
So it depends how the attacker has implemented his attack. So if he is using more SYN parameters, then it will be a SYN attack. If it is an acknowledgement, more he is using so even in the same case, echo reply and echo request. So it is not compulsory that I can use only one or only two, or I can just use any one also. So it depends upon the way the design, how the attacker is launching the attack. So when I wrote a script in the SCAPI, I took both echo and reply. So echo and reply, again, it exhausts the server's memory very fast, rather than asking it to go for only one. So that way I can make it very quick to crash, make the server crash. And of course, it depends upon what type of fragments and what type of size of the packets you are sending. If you are sending a large packet, then obviously with one echo reply or echo request, you can just manage that. So in the similar way here also, SYN or acknowledgement depends upon what type of attack you want to launch. So if you want to launch only one, making it a larger one with a big size, fine. If it is both you want, fine. Yeah.
So is this like the difference between stated and like stateless like connections, right? Is what you're saying? Because if you're in a connection with a state, right? So you have like a slow low-risk attack, for example.
So state or stateless, because ICMPv6 is a stateless.
Stateless.
Yeah.
Okay. Okay.
So there is no question for state.
Okay.
Am I right? Connection.
Yeah.
So then,
Nice.
yes, please.
Going back to one of the slides on the IP version 4 versus IP version 6, was there a study on RNN GRU for the IP version 4 yet?
No, I haven't.
No, not you.
Actually, most of the research, what I'm going to say is most of the research, they had focused on IPv4.
Yes.
ICMPv6 is very less.
Did you show the results of the IP version 4?
No, it's only for ICMPv6.
For you?
No, ICMPv4 is also there.
It is.
That is for the datasets I had taken from NSL-KDD and then Mendeley datasets. These both are IPv4. So you got that model on that IPv4 also.
And it was better.
Yeah,
Okay, got it.
it's better than the Asia Ahmed,
Got
that author's results. Yeah. What I can just show you guys.
Yes.
Fine. You can see this.
One more.
These are the datasets that I had used. So I specifically I had mentioned. So ICMPv4, ICMPv6 is the Sain Malaysian. So you got RNN and GRU also 80% and 95.06%.
Yeah, so my point is,
Yeah.
you know, maybe it's not anything to do with what you coming back. The RNN GRU appears to have, in general, lower accuracy on both the IP version 4 and the IP version 6. So it might be,
From here again, it's okay, it's only a ICMPv4 6, no, it's only 6. So it's only ICMPv6.
oh, I see, okay.
Yeah.
I got it.
So here we have a little bit higher than what Issa Ahmed has got in IPv4.
Got it. Good.
Yeah, I hope I clarified
Yeah,
your,
okay.
yeah. So guys, any more questions?
I think we're good now.
Yeah, yes, thank you very much. And I once again thank you all for bearing with me, and sorry if I had caused you any inconvenience. Thank you very much once again.